All right, let's talk about signal to noise and defining the noise region in the chromatogram to determine the signal to noise for a particular compound. Specifically, let's take the example of chlorotrifluorotoluene. And in this case, here is the signal, as you can see right over here in red. And I've defined a noise region in the method that's going to be used to determine the noise and thus calculate the signal to noise. All right, here we are in the quant method editor looking at 4-chlorotrifluorotoluene. Here's the calibration table. Now, how do I set up the noise region for the signal to noise calculation? Well, I'm going to go over here to Advanced Tasks, and I'm going to go down to Signal to Noise Setup. And you'll notice for this compound that the noise region has been defined. 14.6 to 15.2 is the retention time region I'm going to use to determine the noise. I've also picked peak to peak as the kind of calculation that I'm going to use. So let's go back to see what that looks like in Batch at a Glance. Here I am in Batch at a Glance, and I'm looking at the signal to noise calculation here in this column. I'll sort it on signal to noise against the final concentrations as well as the responses. And you'll see as I move through the responses of the high calibration samples all the way to the low calibration samples that the signal to noise generally makes sense. Let's take a look at that in a little bit more detail. Here is the data put into a slide to see a little bit better, the expected concentrations from the levels and the associated signal to noise calculations here. Now, if I want to graph that out, I've done that in Excel here, and you can see that it follows along reasonably well. There is an issue with level 8 here in this graph. Generally speaking, you'd expect the signal to noise to get better as you move up the concentration curve because you have stronger signals relative to the noise. Hope that helps you define your signal to noise calculations in a more robust and exacting manner.